Hi, my name is Hamza Khan and this is my assignment 4. So the first thing I did was import all the libraries I need for this project. I started with TensorFlow, which is a really popular deep learning framework. I'm specifically using the Keras API, TensorFlow, to build inside and train my models. And for splitting my data into training and test sets, I use train test split. And finally I imported NumPy, and next I loaded the CIFAR10 dataset using TensorFlow's built-in dataset. So it is a set of 60,000 small color images categorized into 10 classes like airplanes, cars, cat, and so on. I split the data into training and test sets right away. Then I normalized the pixel values by dividing by 255 just to scale everything between 0 and 1. And after that, I split the original training set into a smaller training set and a validation set. The validation set helps me see how well the model is doing on unseen data while it's still learning. I use 20% of the training data for validation. And now it's time to build the model, and I used a sequential model, which is just a fancy way of stacking layers one after the other. The first few layers are convolutional and max pooling layers, so they help the model learn special patterns in the image like edges, texture, and shapes. So after that, I flattened everything into a one-dimension array and passed it through a couple of dense layers. And the last layer has 10 neurons with a softmax activation, which means it outputs probabilities for each of the 10 classes in CIFAR10. And next, to make my model more robust and help it generalize better, I added some data augmentation. This basically means I'm artificially expanding my dataset by applying normal transformations to the image during training. So here, I used a simple sequential layer that randomly flips images horizontally, rotates them a little, and zoom in slightly. These changes make the model less likely to overfit and more likely to perform well. And when we go down now, here I created a second model that's kind of intentionally set up to overfit. It has a lot of filters. Two convolutional layers with 128 filters each. The issue with this setup is that it's really powerful, but without regularization or argumentation. It can just memorize the training data instead of learning to generalize. And I compiled the model using Adam Optimizer, which is a good default for deep learning task, and used sparse categorical cross entropy as the loss function, since I'm dealing with multi-class classification. And now I'm training the model using the fit functions. I passed in the training data, the labels, and also included the validation set, so I can track how the model performs on data it hasn't seen during training. And next, now I'm building a second model, but this time I added regularization and data augmentation to help prevent overfitting. I started by applying the data augmentation layer right at the input. Then I added two convolutional layers with 64 filter each. And I also added a max pooling layer to reduce the spatial size and keep only the most important features, followed by a dropout layer with a 30% drop rate. And after flattering, I added a dense layer with 256 neurons, also with L2 regularization, and another dropout layer. this time with a 50% drop rate. And finally, I used a softmax output layer with 10 neurons, one for each class, in the CIFAR 10 dataset. Now I'm training the regularized model, and after training the I evaluated the regularized model on the test set, data the model has never seen before. I used evaluate to get the loss and accuracy. Then I printed out the test accuracy just to see how well the model performs in the real world, and this gives me a good idea of whether all that regularization actually help reduce overfitting, and it usually does. And next I created a helper function called plot history that plots both the loss and accuracy curve for each model. This helps me compare how each model is performing throughout training. I have set up two plots. The first one shows how the training and validation loss change over time, and the second one shows training and validation accuracy. And each model results are plotted with a label, so I can clearly see how they compare. And finally, now I'm using the plot history function to compare the loss and accuracy curve for both the ORFIT and regularized models.